Okay, we'll take a look at the normal distribution. Quick review of this particular information. The first place we started with this particular unit was a density curve, and remember the area under any density curve is 1. Well, the standard normal curve is a density curve, and if it's the standard normal curve, it's a mean. The mean is going to be right at 0 with a standard deviation of 1. All right, so this is 1 standard deviation, 2 standard deviations, and 3 standard deviations. We go -1 standard deviations, 2, and 3 below. So in other words, it'd be at 0, 1, 2, 3, -1, -2, -3. And what this is really good for, a standard normal curve, that's the one that's associated with z-scores, or the z-table that is provided for you. One of the big things we learned in this particular unit was the empirical rule, and remember that sometimes is also referred to as the 68, 95, 99.7, because 68% of the data is within 1 standard deviation, 95% of the data is within 2 standard deviations, and then 99.7% of the data is within 3 standard deviations. Excuse me, went too far there. Is within 3 standard deviations of the mean. Calculating a z-score, this is the first time we saw this. Remember, this was, one way to look at this, it's the observed value minus the predicted value over the standard deviation. Now, typically, you'll also see this written as the statistic, which would be x bar in our particular case, minus the parameter. That's on the formula sheet. And the parameter here is just your mu. So to find a z-score, they're going to give you what's the probability that it's over 250 pounds, or more than 2 tons, or a score of 90? What's the probability that a student scores below a 90? So they're going to give you some cutoff, and that's what's going to go with your statistic, or your observed value. One way this ties back into all of this, to all the testing and everything we did with sampling distributions, you could think about this particular unit as all these being a sample size of 1, which means you're doing sigma divided by the square root of 1, which is just sigma. So one way to think about this, if you want to use some of your testing knowledge, that standard deviation, we're just doing a sample size of 1. Quick reminder on the calculator, if you know the critical value and you're looking for a probability, if we know the cutoff, that's where we're going to use normal CDF. This is just for z-scores, remember. And it's going to be lower bound, upper bound, mean, and standard deviation. Now, if you find the z-score is going to go as either the lower bound or the upper bound, and that depends on the situation, the context of the problem. But you could use that normal CDF with a mean of 0 and a standard deviation of 1. You could use your z-score if you wanted to. But as we'll see in just a minute, you can plug all the data straight from the problem in and not have to worry about it. So that's when you use normal CDF, right? That's when we're looking for an area. And another way, you're also trying to find a probability or a percent. Well, sometimes you already know the area, you know the probability, or you're asked, what's the score that puts you in the top 10%, something like that. So in other words, you know the percentile and you want to find the cutoff. Well, this is where you're going to use that inverse norm function. And then you're going to worry about what's the area that you're interested in, and then the mean and the standard deviation. So recall that inverse norm always shades down, so that's something to be aware of. And we'll see some examples here in just a minute. So if we turn the page, so here's one particular example. In a recent year, the mean test score is 290 and the standard deviation of 37. So assuming that scores are normally distributed, that means that we can go ahead and use our information here. Find the probability of students scored higher than 320. So we're going to let x equal a student score. And all I'm really doing this for is, it's always good if we're going to write a probability statement that we define what variables we're using. So if you recall back when we were doing this, my observed value is 320, my mean was 290, and my standard deviation was 37. And what I was talking about before, it kind of connects back to all the testing stuff we've done, and it's a student. So really, if you think about this, if you divide by the square root of 1, it's not going to change anything. But we'll keep it simple for now. So just for the sake of completion, we'll go ahead and get the z-score. So 320 minus 290 over 37. So in other words, what's the probability that someone is just under 1 standard deviation away? If you remember all this stuff. So if I draw my standard normal curve, I'm very, very close to 1 standard deviation away. So I'm looking for that area right there. So I'm 0.81 standard deviations above. In the calculator, I like to draw that curve because it reminds me. So in the calculator, it's normal CDF. The lower bound's going to be 320. The upper bound's going to be infinity. And I have a mean of 290 and a standard deviation of 37. So we go to the calculator. And that probability is 0.21. So in other words, the probability that a student scores higher, that student, always good to write your answer in context, higher than 320 is 0.21. So there's your answer in context. Sometimes it could be one of these between 250 and 300. So again, we'll let x equal student score. And we can go ahead and find the value right away. So we're looking for now the probability that x is between 250 and 300. So that's normal CDF. The lower bound this time is 250. The upper bound is 300. My mean is 290. My standard deviation is 37. And it's always nice for an AP grader to see that you know how to plug stuff in and find the z-scores. So we're going from just over 1 standard deviation below to 300 minus 290, 37. So really, this particular problem, if we drew it out on a curve, would be just below 1 standard deviation there and barely past the mean. So we can start to get a feel for what our probability should be really, really close to. Just kind of ballparking it with our empirical rule. That way we make sure that we don't get anything strange. And sure enough, this is pretty close to what we would expect, about 47%. So probability score is between 250 and 300 is 0.47. All right. What percent of students had a score greater than 250? So again, this time we're just going to let x is going to be percent of students. Excuse me. No, that's not true at all. X is still going to be student score. And this is really not any different. We're just looking for the probability x is over 250. Well, here's the thing. We just actually got a z-score for 250. And that is negative 1.08. Let me clean that up a little bit so you can read it. And just so we make sure that we're thinking along the right ways, we want to go greater than that. So we're just below 1 standard deviation below. Using the empirical rule, we know from here out is 50%, and then another 34%. So we should be just over 84%, if I'm not mistaken. So we'll do our normal CDF. My lower bound this time is 250. My upper bound will be infinity. The mean, again is 290 with a standard deviation of 37 points. And so from 250 to infinity. One thing that you could do, since they mentioned that the scores can't go above 500, you could put the upper bound as 500, but it's really not going to affect what's going on here. So sure enough, that probability is 0.86. So 86% of the students should have scored above a 250. So here's where we're going to use that inverse norm now with number 4. What is the lowest score that would place you in the top 5%? This is going to be one that you really probably want to go ahead and draw that curve, because again, the top 5% shades to the right. Now we know this is 0.05, and we're looking for the cutoff. So the trick, though, where inverse norm always shades down. So if we want to get that, we need to go 0.95. The mean here is 290, and the standard deviation is 37. So we could use our inverse norm function very quickly. Again, I'm having to use that 0.95 because this always shades down. So the score here would be a score of 350.86. You could say a score of 351. So put it in context, score of 351, put student in top 5%. And you don't even have to round, you could just say 350.86. And then again, what's the highest score that would put you in the bottom 25%? So again, I think it's worth drawing the curve real quick. I'm just kind of thinking, so bottom 25%. So now we know this area is 0.25. So at this point, everything's good with inverse norm. We don't have to worry about flipping anything around. We just go from 0.25. There's your mean of 290. And then the standard deviation of 37, 265.04. So a score of 265.04 is bottom 25%. And one final question. If 2,000 students are randomly selected, how many would expected to score below 280? So in other words, let's just find what's the probability that X is below 280? Well, let's just normal CDF. Let's find a percentage. So this time we're going below 280. So did we do 280 already? I don't think we did. So we're going from negative infinity up to 280. So we're just below the mean here. All right. We're not quite a full standard deviation away. So we should be a little bit below 50%. So we can figure out what percentage of students we'd expect to have that value. Which is 39%. And at that point, I do the 39. So we'd expect 39% out of the 2,000. So we'd expect approximately 780. And if you didn't round before, you might have gotten 780, 6.95 or 787. So either way, just kind of show your work. About 780 students we'd expect to have a score less than 280.